Hello everyone, welcome to the final of the 6 main topics in National 5 Physics. So this is the dynamics topic that we're going to be looking at. I know we've done it slightly out of order. This week's material is primarily going to be revision from stuff that you did in third year physics. Now I know not everyone did this in third year, which is why we are taking the time to give this as a full week's worth of material. So you've got your fill in the blank sheets, which you can add to. The one thing that is not fill in the blanks, where there are examples, I would like you to copy them out and write them into your jotter, so you have practice actually writing the equations down, because that is important. It's a skill that you need to get into, and you need to have also practice at it for whenever we get back in the school building and start doing other assessments again. Or even if we end up in a situation where we need to do remote assessments, then again you will still be expected to write the formula. So I'll give you a heads up when that's happening and when I'd expect you to write something down. But for now, let's move into dynamics. So first thing we need are a few definitions. So speed is defined as the rate of change of distance. Now, rate of change basically means that it's happening in a set amount of time. So it's the change of distance per second, which is why the unit of speed is meters per second, because it's the distance travelled, distance measured in meters, that we travel in a unit of time being seconds. So speed's the distance travelled in a unit of time, but it's defined as the rate of change of distance. Something that we again are going to be looking at a bit more is the difference between average speed and instantaneous speed. If we've got average speed, you end up having a bar sitting on top of the V. That is one of the least important things you have to worry about. So long as you have the V for speed, you do not need to have the bar there. I am teaching you this because it's part of the course, but I'm telling you this is not something you need to worry about. My advice is never write in the bar, because if the bar is missing, it doesn't matter, you get the mark. If the bar is included at the wrong time, you will not get a mark for the formula. And if you don't get the mark for the formula, you will not get the mark for anything else that comes afterwards in that question. The average speed of the object given average speed is equal to distance over time. Distance is measured in meters, time is measured in seconds, and the average speed is measured in meters per second. So, our first formula is that we have distance is equal to average speed times time, where distance is measured in meters, time in seconds, and average speed is in meters per second. And this equation is one of the ones that you will find in your data book. Now, to find the average speed of an object, we have to measure it over a certain distance that it's travelled. Again, one of the ways that we could do that is we could have a stop clock, we could measure a meter stick, we get it to travel past multiple markers, and basically we time how long it takes to travel between the first block and the second block, and the time it takes between those two is our time. We've got our distance, which could either be a full meter or a kind of certain distance along the meter stick. And then we just do distance divided by the time it takes to get between those two markers, and we have our average speed. Now, in the time it took the car to travel between the first and second marker, it could have been accelerating, it could have been decelerating, it could have done a bit of both. You know, if you're thinking about a car travelling down the motorway between two average speed cameras, it could go at lots of different speeds. But the point is that we can figure out what the average speed is between those 2 points. So what we need to do is we just think about what the distance between the markers is our distance, and divide it by the time on the stop clock. Now, you do have a few examples here. So these are the ones which I want you to write out anytime that we're at something which is talking about examples and we end up having blue text coming up. You should be writing this down in its entirety. An athlete runs a distance of 200 metres in a time of 25 seconds. What is their average, or their mean, if we want to use the maths term, speed? Well, the first thing we always do in physics is we always write down the formula. So we've got that distance is equal to speed times time, so d equals vt. Then we substitute in the numbers, so 200 metres is our distance, that's going to go in where d is, equals the v bar is what we're trying to find, so that stays the same, times t, which is now 25 seconds. So we've got 200 equals v times 25, and then we can rearrange it. You don't need to put in the rearrange step. I've stopped putting that in later on, but at least for the first few I've got it in there. What you do need to have is that v bar is equal, or v equals 200 over 25, which is equal to 8 metres per second. Remember, you need to include the units, otherwise you lose out on your final mark. Okay, so if the athlete runs for 30 seconds at an average speed of 6 metres per second, how far do they travel? Well, this time it's actually a bit simpler because we've got d equals vt. We're actually trying to find the distance. So it's just distance is equal to 6 times 30, which is equal to 180 metres. Then for part C, how long will the athlete take to run 10,000 metres at an average speed of 5 metres per second? Well, again, we've got our d equals vt, we've got our 10,000 equals 5 times t, and we rearrange through, we end up getting 2,000 seconds. I've got a number of examples here which you can try. These all already have the standard units associated with them. These are not ones that you would be expected to write down. These are the ones that I'd get you to do in class. Okay, so with time equals distance over speed, so that is 14 divided by 2, so we get 7 seconds for the first one here. Then our distance is equal to speed times time, so 340 times 3, so that equals 1020. If we're trying to find speed, speed is distance over time, which is 1 divided by 1, so speed is 1 metre per second. Remember, that's where the definition comes from. Okay, if you're travelling at 1 metre per second, you've travelled a distance of 1 metre in 1 second. If you're travelling at 50 metres per second, you travel 50 metres in 1 second. Okay, then we've got distance equals speed times time again, so that means that 50 times 3 is 150 metres. And this last one we're dealing with the speed of light, which is 300 million metres per second, and the distance is 400 million metres. Incidentally, that is the actual distance from the Earth to the Moon. So this tells us how long it takes for light to get from Earth to the Moon or from the Moon to Earth, which comes out as about 1 1/3 seconds. Another thing which you need to know is you need to know how to convert kilometres per hour into metres per second. If a car travels 150 kilometres in 2 hours and 45 minutes, find the average speed of the car, first of all in kilometres per hour and then in metres per second. Well, kilometres per hour is fairly straightforward because we've got our d equals vt. Our distance is 150 because it's 150 kilometres. Now remember, it's 2 hours and 45 minutes is not 2.45 because 45 minutes is 3/4 of an hour, so it's 2.75. So then we get our average speed as coming out as 54.5 kilometres per hour. It's important the units are km/h⁻⁻1 or fully written kilometres per hour. It's not kph or anything like that. You have to use the correct units. If in doubt, just write it out in full words. Now, metres per second, slightly more complex. We have to basically multiply it out so that we've converted our 150 meters into kilometers, which is 150 times 1,000. And then we have to convert our 2.75 into seconds. 2.75 hours in seconds, so we multiply it by 60 to turn it into minutes, multiply it by 60 again to turn it into seconds. And that ends up giving us 150,000 is equal to V times 9,900. We rearrange that, and we get our average speed as equaling 15.2 meters per second. Now, I'm going to tell you a cheat here. The cheat is, if you want to convert kilometers per hour into meters per second, divide by 3.6. That's it. Kilometers per hour, meters per second, all you do is take your number in kilometers per hour, divide it by 3.6, and you now have your value in meters per second. And it works the other way around. If you want to convert up to kilometers per hour, take your number in meters per second and times it by 3.6. Now we also have to have instantaneous speed. The thing is, it's really difficult to have instantaneous speed. It doesn't really exist. Because in order to know the speed of something, you're kind of usually measuring a time. The closest we have to instantaneous speed is the dial of the speedometer in a car. But even a speed camera that takes the speed that you're travelling at a specific point in time as you go past it, if a car is speeding, the reason you know, particularly at night time, you've been caught speeding is that you see two bright flashes from the camera. And those two bright flashes are the two photographs it takes, and it works out an average over a very small amount of time. Okay? That's really the difference. Instantaneous, it's not really instantaneous speed most of the time, it's just over a very small amount of time. So if we were going to be doing that in our lab, we would be using a light gate. We'd have a trolley with a wee card on it, and rather than measuring over distance, we'd just measure how long it took the car to pass through the light gate. That's how we'd do an instantaneous speed measurement. So instead of using a ruler and a meter stick, we'd just use a set of light gates. And experimentally, the way this tends to work is that our instantaneous speed is the width of the card divided by the time in the timer. Mathematically, there's no difference between them though. Okay, acceleration. Now, acceleration is another kind of big one to make sure that you know. This one is one of the more complicated formula to rearrange and deal with in National 5 Physics because there are 4 terms. Okay, so acceleration is defined as the rate of change of speed. Okay, so there's a change in speed divided by time. So acceleration is the increase or decrease in speed in a unit of time. Change in speed over time taken. Sometimes that's referred to as delta V, so you might get told the change in speed is a certain amount, and you can put that on the top and divide it by the time that you're given. More often, though, you're given a final speed and an initial speed. And we have our actual formula here as A equals V minus U over T, where V is the final speed in meters per second, so that's the one which it has finished at. U is the initial speed, T is the time in seconds, and acceleration is in meters per second, or meters per second squared. The unit for acceleration is the meter per second, or meter per second squared, which you can see it's written down there. It's written as ms to the minus 2. Now, some of the terms you need to get used to are uniform or constant acceleration. That means that it has the same acceleration constantly. You could have something with an average acceleration, that's fine, but usually you will be dealing with constant or uniform acceleration. Definition-wise, we've got down here that if the acceleration is 10 meters per second, the speed is increasing by 10 meters per second every second. If the acceleration is minus 10 meters per second, then the speed is decreasing by 10 meters per second every second. If the acceleration was 20 meters per second, then the speed would be increasing by 20 meters per second every second. So here's one of the acceleration examples. A car accelerates uniformly from rest to 40 meters per second in 20 seconds. We are to calculate the acceleration of the car, or to find out how long it took to reach 15 meters per second, and to find the speed after 12 seconds. Now, the first thing we need to think about is the vocabulary of the question. It's accelerating uniformly. That means the acceleration is constant. And it's accelerating from rest. Rest means zero. Rest means that you're staying still. So rest is sometimes you're accelerating from rest, sometimes you're braking to rest. If it's rest, the number is 0. So we're first to calculate the acceleration. Okay, so we've got the different parts here. So again, first thing we always do is put in the formula. Our formula is A equals V minus U over T. Then we substitute in the numbers. Well, A is what we're trying to find. V is the final speed. So that's the second speed that we've got here. So it's gone from rest. So that means it started at rest. Rest was the initial speed, and it's gone to 40 meters per second. So 40 is the final speed. So it's A is equal to 40 minus 0 divided by the time, which is 20. When we put that in, we get that it's 2 meters per second as our acceleration. Now for B, we're being asked how long it took to reach 15 meters per second. Now we have been told the acceleration is constant. That means the acceleration is the same the entire way from 0 until it's got to a speed of 40 meters per second. So we now know that the acceleration is 2 meters per second. So we're going to use A equals V minus U over T again. This time we've been told the acceleration is 2 meters per second because we've worked it out. Know that the speed that we're looking for, the final speed, is 15 meters per second. Our initial speed is still 0 because it still starts from 0, and our T is what we're trying to find. So we rearrange that. T is equal to 15 over 2, which means it was 7.5 seconds to get to 15 meters per second. And then finally, what was the speed of the car after 12 seconds? Well, again, we know it was a constant acceleration. We now know it's 12 seconds we're looking for, but it's still starting from rest. So A equals V minus U over T. This time 2 is equal to V minus 0 over 12. And then V equals 2 times 12 gives us 24 meters per second. That was the speed after 12 seconds. We could look at it another way. We can look at this time something when it's actually slowing down. So a car is travelling at 30 meters per second. So that means that's the initial speed. It brakes, and after 5 seconds, the speed of the car is now 10 meters per second. So calculate the acceleration of the car. Well, again, we put in our formula. Now this time, V will be 10 meters per second because it has slowed down from 30 to 10. So V is 10, U is 30, and T is 5 seconds. So A is equal to 10 minus 30 over 5, which gives us an acceleration of minus 4 meters per second per second. Okay, and then how long does the car take to stop? Well, we're kind of using an average acceleration here. So again, we've got our A equals V minus U over T. Our acceleration we now know is minus 4 meters per second. And take to stop, that means take to come to rest, which means the final speed we're looking for is 0. So V will be 0. Our U, we start at 30 meters per second, so our U is 30. So we've got minus 4 equals 0 minus 30 over T. We rearrange that, and we get T equals 0 minus 30 over minus 4. We put that into the calculator and it comes out as 7.5 seconds to come to a halt. Okay, an F1 car accelerates to 100 kilometers an hour from rest in 2 seconds. Calculate the acceleration in meters per second per second. Well, we do have an issue here. Can any of you spot it? The speed. the car accelerates to 100 kilometers an hour from rest to 2 seconds. Kilometers an hour is not a speed we can work with. We have to know what kilometers an hour is in meters a second. So we know that there are 1,000 meters in 1 kilometer. Good. Makes it easy. 100 kilometers an hour is therefore 100,000 meters an hour. And 1 hour, there are 60 times 60, so 3,600 seconds. So 100,000 divided by 3,600 gives us 27.8 meters per second. 27.8 meters per second being the same as 100 kilometers per hour. And maybe one or two of you remembered what the trick was to convert the 100 to 27.8 really quickly. Divide by 3.6. So you could have just divided by 3.6 to do that conversion. However, once that conversion is done, we now know that the speed we're looking for is 27.8 meters per second. So A is equal to V minus U over T. A is 27.8 minus 0 divided by 2, and that gives us an acceleration of 13.9 meters per second per second. That's the acceleration, the average acceleration of an F1 car that can get to that speed, that fast. Acceleration setups are far more complex. Basically, we need to be able to measure the instantaneous speed at 2 separate points, and we need to know the time it takes to get between those 2 points. When we get back into school, we'll be able to show you that in more detail. Speed time graphs. This is, again, something that you would have dealt with all the way back in third year physics. So we've got speed on the y-axis, time on the x-axis. Please, under normal circumstances, include units. So these are not included here, but that is for convenience. Anytime that I am drawing them in terms of answering a question, they will have them there. But that's to show that it doesn't really matter what the speed is or what the unit of speed is or the unit of time is. For these, we could be dealing in hours, seconds, minutes, decades for measurements of time, and speed could be in meters per second, kilometers an hour, furlongs per fortnight. It doesn't really matter, so long as it's a speed on the y-axis and time on the x-axis. A stationary object will still give you that kind of flat line along the bottom, telling you that it is not travelling anywhere as time is moving along. If it's speeding up, the line is going to have a gradient that would be positive, linking into some maths there. If the object's slowing down, it would have a gradient that is negative. And if the object has a constant speed, it's, well, sitting completely flat. The thing is, speed time graphs are really useful. We can use them for a bunch of things. And we're going to have a look at them just now. So basically, we can use speed time graphs to monitor speed of an object as it's travelling on some kind of journey. And we can use it to find the distance travelled by an object during a journey. So even if it's got kind of changing speeds, as long as we can find the area under the graph, we can find the distance that's been travelled. And finally, another one is we can use the gradient of the graph to find the acceleration of the object at any given point. So this is kind of what it ends up looking like. We get what's called a speed time graph, which we can split into different shapes. Basically look for triangles and squares. So we've got this speed time graph that I've split into 3 sections, A, B and C. And basically what we'd do is we'd find the area under each part of the graph. For part A, we'd use a half BH. So half base times the height. The height is 20, base is 20, and we find a half because a half BH is the area of a triangle. We do length times base for B because, again, that's how we find the area of a rectangle. And for c, we do a half base times height, because again that's how we find the area of a triangle. One thing you need to be very careful of is the numbers on the axis for time. We're looking at the change in those numbers. So for example, when you're looking at b, the number for the base is not 35, because, well, the entire base isn't 35. The base is the difference between 35 and 20. So it's 15 is the base and 20 is the height. Okay, so this is the kind of more text-driven version of the description, which I'll let you have a chance to read through, but you've got this in your notes anyway. And basically, once we get to the end and we've calculated the area under each of those objects, we find the distance by adding the areas together. So as I said, whatever the shape of the speed time graph, the distance travelled is the area under it, and the acceleration is the gradient of any given section of the graph. So I'm going to do one quite complex question here to show you how this works. Okay, so a car accelerates uniformly from rest to a speed of 30 meters per second in 15 seconds. The speed remains at 30 meters per second for 20 seconds, and then the car decelerates uniformly to rest in 5 seconds. Now, I'm going to remind you once more, this whole section I would like you to copy out. This is not in your notes. I want you to have all this copied down because I want you to see where this comes from. So, for part A, you're being asked to sketch a speed time graph to represent the journey. Now, it's important to sketch. In physics, you still use a ruler, but when you're doing a graph which says sketch, you only need to include the numbers that are important to get the information from the graph. So, sketch a speed time graph to represent the journey. First of all, we need our axes. So we've got our y-axis and our x-axis drawn there. Now we need to make sure that these are labelled. So our speed is in meters per second, our time is in seconds. You will not get the marks if you don't put that in. We know it's accelerating from rest to a speed, the speed staying constant, and then it's decelerating to rest. So we've got our kind of shape in like this. The scale is not important if it's a sketch. Just the fact that it is neat, drawn with a ruler, and you have included the numbers. So the numbers we need to include are on the axis for time, 0, 15, 35 and 40. And on the speed axis we need to include 0 and 30. So 0 is just there as the origin. And then we can check that it does what it's telling us. So it accelerates uniformly, so a straight line going from 0 to 30 meters per second as a speed in 15 seconds. It then stays at 30 meters per second for 20 seconds. That's going from 15 to 35, so that is a difference of 20 seconds. And then the car decelerates uniformly to rest in 5 seconds, which it does. So that is our graph. And sketching that would normally be worth 2 marks. So, question B, calculate the initial acceleration of the car. Well, it's gone from rest to 30 meters per second, so we know we're going to be using A equals V minus U over T. When we substitute in the numbers, our final speed was 30 meters per second, our initial speed was 0 because we were at rest, and it took 15 seconds to do that acceleration, so A equals 30 minus 0 divided by 15, and that gives us 2 meters per second squared. And then there's the final acceleration of the car, which was actually when it came to a stop, so V is 0 this time. The initial speed is 30 and it only took 5 seconds to stop. So again, A equals V minus U over T. A equals 0 minus 30 divided by 5, and that gives us minus 6 meters per second squared. Now, both of these questions would normally be worth 3 marks each. One formula, one for the substitution, and one for the final answer with the unit. Calculate the total distance travelled by the car. This is another question that's worth 3 marks. And I've pulled up this graph because we need to use a slightly different formula for this. The distance travelled by the car is found by d equals area under the graph, because the speed is changing. You do not have a way of being able to deal with that at this point in time otherwise, so we need to use d equals area under graph. That's your first mark, by the way. Then, well, there's 2 triangles and a rectangle here, so d equals a half length times height, plus length times height, plus a half length times height. So that's for the triangle, the rectangle, and the triangle. For the first triangle, the base is 15, the height is 30. In fact, the height is 30 for all of them. Then for the rectangle, we're adding 20 times 30. And then for the last triangle, we're adding a half times 5 times 30, because, again, we've got 30 is the height. It's only going from 35 to 40, so only a difference of 5 in time for the base. And it's a half because it's a triangle. And that substitution, that is your second mark. And your third mark is for saying it's 900 meters. Finally, we are asked to find what is the average speed of the car. Well, distance equals speed times time. We've calculated the distance was 900 meters. The time we've got, because the time was the maximum number in the graph, it went up to 40 seconds. So then V is 900 divided by 40 is 22.5 meters per second. Okay, everyone, I hope you all have a good week.